Okay, let's do this. We're going to do an electric field due to a charged disk. Now, I already did this. I calculated the expression for the electric field due to a disk along the axis of the disk, and that wasn't too terribly bad. But I want to find the electric field. I want to really do two things. I want to do this numerically so that I can find the electric field anywhere, and then I want to show how close you have to be to have a constant electric field. So one of the things about a disk like this is that we use this in a capacitor, and the electric field is fairly constant in magnitude and direction if you're near the center. And so how close do you have to be, right? If you use your normal analytical expression, and I'll include the link down below for how to get that, that's only on the z-axis. Okay, so how do I do that another way? So let me skip over here to the paper, and then we'll talk about this and how to do it with the computer. Okay, so first of all, let's just go over some important things. Here is the electric field due to a point charge. So if I have a point charge right there, and I want to find the electric field right here, then I need these two vectors, the location of the point charge, the location of the observation location, and the vector r is from the charge to the observation location, and then this is the electric field due to a point charge. Okay, 1 over 4 pi epsilon naught is just a constant. The charge, the distance from here to there squared, and then r hat is a unit vector, so I can get the direction of the electric field as a vector. So that's fine. And then what I did, what do you want to do for a ring? If I have a ring like this, then I just break this, and this is the x, and this is the y, and then so z would be coming out of the paper. I can just break this into little points like that, and each point has a corresponding point on the other side, such that the only electric fields that don't cancel are in the z-axis, and then you can integrate. It's not so bad, and you can do that. I also did this by breaking this into actual, let's say 100 point charges, and calculate the vector electric field for any location, because it doesn't cancel in the non-z direction if you're not on the z-axis. Okay, but I did that, and that's down below too. And that's a numerical calculation. And so then if you do that analytically, you get this expression for the electric field due to a ring, which is important for the electric field due to a disk, and I'll tell you why. And then you get this is the electric field due to the disk. This is important because if I have a disk and I want to find the electric field on the z-axis, I can break this disk into a bunch of rings with a radius lowercase r and a thickness dr. And then I can find the electric field just due to this contribution, and then I can add up all the rings to get the total electric field and make a integration. And that's what I did here to get this expression for the electric field due to disk, the magnitude, on the z-axis. Okay, and then from that, I didn't talk about this, but it's fairly constant if you're close enough. If z is very small compared to r, you can actually use this, which is 1 minus z over r, which is an important expression. And if it's really close, then if z is very small, then this is just 0, and you just get this. So it depends on the charge and the area of the disk. Okay, so now I want to, let's skip over here and think about how we're going to do this numerically. All right, so here's my disk. And by numerically, I mean break it into a bunch of small pieces. Here's my disk right there, radius r. And this is the x and the y plane. So the initial idea is, well, hey, you already have the electric field due to a ring numerically. So just use that same code, break this into, calculate the electric field due to a ring. Let's draw this from the side. So here's my disk. Oops, it's a really thick disk, that's fine. And I want to find the electric field right there. Well, I could break this into a disk like that, right? That's this disk from the side, and then use that to calculate the electric field right there. And then just do that same thing make a whole bunch of disks from this, a whole bunch of rings add up to a disk. Well, you know what? That's not going to work. I mean, you could get it to work, but it's not quite perfect. Because if I break this into, let's say, 100 points, well, let's say 10, and then I have the charge, and then I do another loop over a ring over here, I'm going to have to break that into more charges in order to have, because this bigger ring should have a greater charge. So it's not, I can't just throw it in there. I'd have to actually calculate how many charges to put in each ring, and I don't want to do that. I could do that, but I don't want to do that. Okay, so instead I'm going to do this trick. Here's my ring, here's my disk. I'm going to make a point right here, and it has a charge, and it's a random point. It has a vector location R of random, using the random and 0. It'll be a 0 in the Z direction. So, and I can change this up. Actually, we might want to do that in just a little bit, but there is the point. And I can just make a whole bunch of random points, and then they should be evenly distributed, and use that to calculate the electric field. Now, I do have to say, if this is a radius of, let's say I said the radius of the whole disk is 0.5, I said 0.5, then I want to make sure that if I generate a point over here where the radius of this, the distance from here to there, is greater than this radius, then I throw it away. Okay. And then once I have all my points in my disk, then I can just calculate the electric field due to each individual point, and I'm all set. Okay, so this might take a while, but that's what we're going to do. So let's switch over here to the computer. I'm kind of excited. I actually haven't done this already, so I mean, it may or may not work. You just never know. Okay, so there's a computer. I'll keep the video on for a little bit until I need it. Okay, untitled. Let's just first start with k equals 9 times 10 to the 9th. When we're doing a numerical calculation, I have to use numbers, right? So I'm going to need the total charge Q, I'd say 1 nanocoulomb, 1 times 10 to the negative 9th, and the radius R equals 0.05. That's what I picked. Okay. Now the first thing I want to do is I want to generate 1,000 data points. I want to generate 1,000 points in the XY plane, and that way we can see it the best way and see if it looks like it's uniform. Let's just do that. Okay. So I'm going to say n equals 1,000. That's how many I want. And let's do 100. You always want to start off smaller than bigger, because it'll get too bad. And let's say n equals 0. That's how many I've made. So, there's several ways to do that. Let's just do n that way. Okay, so the first thing I'm going to do is to make these points. Let's say for I in range n. This is just going to do a loop n times. And let's just show you how that works. Put that at 10. And let's just say print I. And let's say numerical disk. Save it. Run it. Yeah, so it went from 0 to 9. So that's good. So that's working. That's a good. Let's change that to 100. And let's also put Q's equals a list. Okay, so what I'm going to do is, let's just do it this way. Let's go back to 10. Let's say Q's equals Q's plus rand. That's it. So what this rand is a built-in function in Python that generates a random number between 0 and 1. So this will take that empty list, this will generate a random number, and it will add it to that list. And there's only 10 items in the list, so I can print that out at the end. Let's say print QS. And let's just see if things are working, right? Build things slowly. And it's not. Is it random? I'm sorry, it's not random, it's random. There you go. Now, there are random functions in Python, and there's a random module. But remember, I'm using GlowScript vPython, so it already loaded a bunch of the math things in there. So that's why I'm using random. And all these numbers are between 0 and 1. Okay, that's important because I actually want numbers between negative 0.5, 0.05, and 0.05, right? Because that's the space of my disk. So how would I do that? Well, let's do this. 0.05 times 1 minus 2 times that. So if I do 2 times a random number, then this could be anywhere between 0 and 2. And so if it's 0, on one end, I'd get 1 minus 0, so the largest number. If it's 1, I'd get 1 minus 2, I'd get negative 1. So this expression here goes from 0 to from negative 1 to 1. And then if I multiply that by 0.05, then I should get values between 0.05 and that. And let's just call this, let's just change this to R. That way it makes more sense. And you'll notice all those numbers are between negative 0.05 and 0.05, so that does indeed work. Okay, but we don't want random numbers, we want charges. So let's do our charges. So I'm going to say, instead of just that, I'm going to say sphere position equals vector that for the x value. Let's see, wait, and that one is, okay, yeah. Same thing, r times 1 minus 2 times random for the y component, and then 0. Okay, and that should be another parenthesis. Wait, is that right? Yeah. Okay, and then I need another parenthesis right here. Yeah. Okay, and now I need the radius. Let's give it a radius of, let's see, if the disk is 5 centimeters, let's say 0.002. I don't even know what that was going to look like. Okay, let's just run it. And something bad happened. 3 arguments. Vector 1, 2, 3. Oh, I missed a parenthesis right there. Right there. I think I'm bad with parentheses right now. I made another mistake. Okay, so I have. Let's just pull this over. Position. Okay, that goes with that. And that goes with that. And then 2. Oh, I got an extra one now. There. There's my disk. Okay, actually it's not a disk. Right, because I just realized I didn't check to make sure it was less than R. So let's actually do this. Let's say R temp equals this stuff. And that goes to here. Yeah, Control X. R temp. Okay. Now I'm going to say if mag R temp is less than or equal to R, then I'll add it in there. Okay, now this is bad because I'm not going to actually make 1,000 points because I'm going to throw away some. So I do need to switch this thing up here. So let's say this, n equals 0, and I'm going to say while n is less than n. And then I will add 1 to n, less than or equal to. I always get that mixed up. Oh, I can't print. I just noticed down here. I'm going to turn off this camera. This object. I was printing out spheres, and it's like, I don't really want to do that. So, okay, I'm missing it. R less than or equal to n. If it's less than that, then I'll add 1 to the sphere, and I'll add 1 to n. N equals n plus 1. Okay, let's see if this works. Okay. So there's your sphere. Now let's put 100. See? That's a disk. It is a disk. Now put 1,000. Check that out. There's my disk. Now I just need to calculate the electric field due to those 1,000 points, and I'm going to be all set. Okay, you see where this is going? It's going to be awesome. It's going to be awesome. Okay, I'm actually going to change this. because I don't actually need to display all those things. Let's actually do this. Let's do Q disk equals cylinder, position equals vector 0, 0, 0, axis equals vector 0, 0, 0 point, how thick should I make that? That was 2 centimeters big. 0.002, radius equals R. Okay, so there I have my disk and my chart. Look at that. That's art. I wonder why they're sticking out on one side but not the other side. Okay, well now I don't need to actually make these spheres. I'm just going to make these as values. So I'm just going to take this away and just add the vector value, the location. Okay, there's one other thing I need. Let's print. Let's do this. Print length of QS. Let's just see if it's 1,000 or 999. Okay, 1,001. Okay, let's do this, 1,000. Okay, so that is good. Now there's one other thing I need. I need DQ. DQ is the charge of each one of those little bitty points, and that's going to be equal to the total charge divided by n. I am ready to rock and roll now. Let's put an observation location. OBS equals, it's a sphere. Let's put it as a sphere. Let's put it on the z-axis. So position equals vector 0, 0, 0.01. Radius equals 0.002. Color equals color.yellow. Okay, so there's my point. That's where I want to find the electric field. It's kind of close. That's fine. And I can now calculate the electric field. So here's how I'm going to do that. Let's say what I want to do is go through each one of these charges in my list of QS. And I want to calculate the vector position from that charge to my observation location and calculate the total electric field. So let's say this, E equals vector 0, 0, 0. All right, that's my starting electric field. And now I can say for, I can actually say for RQ in QS. So RQ is the vector location of each one. I don't have to do anything else. I can say R equals obs.pos minus RQ. That's minus. That's going to be the vector R. That works right. Okay. And then DE equals K times DQ times norm R divided by mag R squared. And then E equals E plus DE. That's it. And let's just say, let's make let's do this. E scale equals 0.001. I don't even know what it's going to be. Print E. Let's just print E. Okay, so it does have a. Okay, these are, that's fine. These are small compared to that. We'll add more numbers in there in just a second. So this is 6,000. So I want to have an E scale of 1 times 10 to the negative 4. Now let's make an E arrow. E arrow equals arrow. Position equals obs.pos. Axis equals E scale times E. Yeah. And then the color, let's make it cyan. Let's make it red. And let's run that. It's too big. Okay, so let's make this 10 to the negative 6. No, it's too small. 10 to the negative 5. Well, that's good enough. Let's make this 10 to the negative 6. 5 times 10 to the negative 6. There. Okay, there's my electric field. Okay, now let's just move this charge over to the edge. Okay, and we're going to make a plot in just a second. Let's move that charge over to the edge, which is pretty easy to do. All I have to do is let's put this at the y value at 0.05. And you'll notice that the electric field is not in the z direction, it is pointing away. I think that works, okay? So we can make a plot of this as it goes down. And I want to do that. What did I want to do? I want to show that it is, that how close you have to be constant. I should probably start switching to a graph, right? This is already a 20-minute video. I think maybe what I should do is stop here. But in that way I can break this into 2 parts. And in the next part, no, I'm going to make this. I'm going to make a plot of the electric field. I'm going to make multiple points. And I'm going to move these points down, and I'm going to make an electric field at different locations just along this axis so we can see what the electric field looks like. So let's do that. So let's say over here, dy equals, let's call it dr. dr equals vector 0, negative, how far do I want to move? I want to move, let's say, if I do a centimeter, I'd have 5. So let's say 0.0050. That's how far I'm going to move. I'm going to start at the top, and I'm going to move down and make a whole bunch of electric fields. Okay, so that's where my observation location starts. Now I'm going to, I should really make this a function. But I'm not going to. Let's say, while obs.pos.y is greater than or equal to negative r, do the following. Calculate E. And you notice I don't have to make all these data points again. I don't have to, I've already generated those. Okay, now plot E. Yeah. Now I need to move the observation location. I actually need to make another observation location. So I guess I need to do it up here. Let's just say sphere position. I'm not going to name them. Position equals obs.pos. Radius equals what did I say it was? Oh, there, 0.002. Color equals color.yellow. There. So now down here, after I make that arrow, I'm going to move my observation location. So I'm going to say obs.pos equals obs.pos plus dr. And I think that will work. I don't need to print E anymore. Let's see what that looks like. Okay. Yeah. Okay, I'm pretty happy, right? Because now you can see that, yes, indeed, the electric field is fairly constant near the center of the disk. Let's just do this. What if I move my observation location so it's more than 0.1 centimeter away? What if it's 0.3 centimeters away? What would that same thing look like? And you can see it's still fairly constant right there. And this is a cross section across that whole thing. And then I can move it even closer if I want to. Let's pay 0.05. And there, you'll notice there's some jaggedness. The jaggedness is due to the, ooh, look at that. So what happens, I think, here is that you can see the randomness in the number of data points I have in there. So that makes it really weird. If I change this to 10,000, let's see what happens. Yeah, Look at that. See, now it's much more even. I'm pretty happy with this whole thing. This is a pretty good program. But like I said, what I want to do is make a graph of this, and then I want to make a graph of the electric field as a function of distance this way, and compare that to the different models of the electric field to the analytical version. But I'll do that in another video because I think this one's already 25 minutes long. Okay, so we have one more. Actually, I want to do that, and then I'll make a third video where I look at the electric field due to 2 disks, and that's a capacitor. Okay, I'm going to end there. And I'll put this code down below, and I'll include the other links. Everything's going to be great. I'll talk to you guys later.